exercise 5 and is on the pendulum period. And this one states the period of a pendulum with length L that makes a maximum angle theta naught with the vertical is, and then we're given this, this giant formula. So capital T equals to 4 times square root L over G, and then times it by the integral from 0 to pi over 2 of dx over square root 1 minus k squared times sine squared x. And again, the period is just the time it takes to go back and forth. So back and then forth is one period. One period. And here, just drew that better there. And so where this k value is equal to sine of 1/2 theta naught. And again, this angle is the angle between where the pendulum is and the period. So this that arc length across there. So the angle with the vertical. And then g is the acceleration due to gravity. And now we're asked in part A, so we have several questions here. We're asked in part A, expand the integrand as a binomial series to show that, so the integrand expand this one again. Whole idea of Taylor approximation is to simplify complex functions such as integrals and square roots and even sine functions. Yes, we're asked to do that. Expand that, the integrand as a binomial series to show that this capital T, the period, is equal to 2 pi times L over G square root, and then times it by 1 plus 1 squared divided by 2 squared times k squared plus 1 squared times 3 squared over 2 squared times 4 squared, and we have this same pattern, 1, 3, 5, all those squared, 2, 4, 6, all those squared, and k, 6. So even though this looks a bit more tedious, but these are all the simple polynomials, just simple constants times it by another constant squared, and so on, and then to the power of 6, and so on. And then, and also in this integrand, we're also given the hint, use the following formula in the derivation, which I may or may not prove in a later video. Yeah, this was a video I should have done years ago. But anyway, so we're going to use this as well. So integral from 0 to pi over 2 of sine 2n to the power of 2n of x dx equals to 1 times 3 times 5 divided by 2 times 4 times 6, and keeps going on and on, top and bottom, all the way to 2n minus 1 and 2n. So notice the 2n, 2, 4, 6, when n is 1 is 2, when n is 2 is 4, and then there's other ones you just subtract 1. So this is going to be 2 minus 1 is 1, and then 4 minus 1 is 3, 6 minus 1 is 5, and then times by pi over 2. And then we're states, if theta naught is not too large, the approximation t approximately equals to 2 pi times L over G squared, obtained by using the only the first term in the series is often used. Yeah, so once we expand this out, so if you just use just the first term, is just this part here. So if we use this one right here, it just corresponds to this using this first term of this approximation. All right. That's often used, but a better approximation is using two terms. That is using these two, like that. And then you'll get this over here. Those are the first two terms. And yeah, let's keep going further. And yeah, these approximations will be for part B and C. We'll get to those in a bit. I'll read those after, or I'll just read them now. So notice that all the terms in the series after the first one have coefficients that are at most 1 over 4. And then use this fact to compare the series with the geometric series and show that this inequality holds over here, and we'll get to that later. And then it says use the inequalities in part B to estimate a period of a pendulum with L equals 1 meter and theta naught equals 10 degrees. And how does it compare with the estimate, the one-term estimate? And then what if theta naught is 42? Anyways, we'll get to those in a bit. Let's just do it one step at a time. So let's look at part A. So let's first write this out in the usual binomial series form. So we want to expand this integrand as a binomial, or expand this integrand, this integral as a binomial series to show that t equals to this. So we're going to have to approximate this one as a Taylor's as a binomial series. So we're already given the binomial series. So let's look at it in our usual binomial series format. So as a refresher, let's just write our binomial series as per usual. So binomial series, binomial, and this helps everything out. Binomial series, yeah, just fix that up. So it's going to be 1 plus x to the power of k. This equals to 1 plus kx plus, the next one's going to be k times k minus 1. And then over, this is going to be over 2 factorial, then x squared. And I'll just move this down. Yeah, just move it down to make more room. And then the next one's going to be k, just a refresher, k minus 1, k minus 2, and then over 3 factorial, and then this can be k cubed plus dot dot dot, and again we have r is equal to infinity. R is equal to 1. So absolute value of x is less than 1. So radius of convergence r is 1. All right. Yeah, so again, we want to rewrite our period to get it in this form so we can approximate using this binomial series. So we have our period is 4, yet t equals to, scroll up to it. Yeah, let's scroll up here. So 4 times square root L over G, then we have this integral from 0 to pi over 2, and then this 1 minus k squared sine squared. So at the bottom, let's just write it down. All right, let's write this down. So 4 times square root L over G, and then integral from 0 to 2 pi of, top is just dx, and then square root 1 minus k squared sine squared x. And now in our usual format, we'll just simplify this out or rearrange it so it looks like the binomial series. So this equals to square root L over G, yeah, 4 times square root L over G, and integral from 0 to 2 pi. And now we could write this in the top. So I'm going to write this as, I'm going to put this a bracket like that. I'm going to put a bracket 1 minus, or actually not the bracket there, I'm just going to put, yeah, so the square root, I'm going to make this a square root power of negative 1 over 2. So it's going to be minus, yes, 1 minus, I'm going to take this, I'm going to put a plus and then put a minus separately like this. 1k squared, just so that we can line it up with our x value. Like that. And then this is going to be all to the power of negative 1/2. Like that, dx. So in other words, this is going to line up with this up top. So this is our k. This lines up with our binomial k, and then our x1 is going to be, well, this whole thing. Let's put this a bit better. So this one's going to line up with this x. Yeah, so then this part is over there. So now we can just rearrange the whole thing. Yeah, and just write this as equals to 4 square root L over G. And now we could write this integral from 0 to 2 pi. And now we're going to need another square bracket. Now it's going to be equal to, so we're going to replace it with this whole thing over there. And we're going to have to save some space. So it's going to be 1 plus... And then we have it over here. Well, actually, no, not just 1 plus. This whole thing gets changed so that it becomes this whole thing. So that's our x, that's our k. So it's going to be now 1 plus k, which is this part here. So that k is going to be a negative. So 1 plus k. Yeah, I mean 1 plus x. 1 plus x. Yeah, I mean 1 plus kx. So it's going to be negative 1/2. 1 over negative kx like that. Times it by. Now we have a minus. This is our x now. K squared sine squared of x, that is our x value. Now it's going to be plus k, which is negative 1/2, times it by, yeah, times it by negative 1/2 k minus 1, so that's going to be a minus 2 over 2, so that's going to be a 2 over 3. And then this is going to be a 2 factorial, and then it's going to be, well, this part here, k squared sine squared x. Yeah, now this part's going to be squared because that's our x value. That's over here. And now the next one's going to be this part over here. And we're going to have some more room. So we're going to have a plus here. Plus k, negative 1/2, times by k minus 1 is negative 3 over 2. Times it by k minus 2 is going to be 5 over 2, negative 5 over 2. Divide this by 3 factorial. Times it by our x, which is negative k squared sine squared of x, and now this is going to be cubed, and then the next one's going to go plus dot dot dot, put a box around that, and that's going to be our dx like that. Alright, so now that we have this, let's just simplify it further before plugging in the sine formula that we were given. So we're going to have 4 times square root L over G times by integral from 0 to 2 pi, and now this next term is going to be, well, it's going to be 1 again. Now this here is going to be 2 negatives, so that's going to be a positive. So 1 plus, now we're going to have a k squared over, or I'll just put a 1/2 instead in front of it. I'm going to put the 1/2 like this because just so it matches up all these other ones. It's going to be plus 1/2. Now we're going to have, I'm going to put this as k squared sine squared. Now this one right here is going to have 3 negatives. So negative, negative, and, well, actually no, it's not 3 negatives because this is negative, negative, that's 2, but this one is squared. So that's going to be positive. So it's going to be positive again. And it's going to be positive like this, and And yeah, I actually made a mistake over here. It's not a negative 2 over 3. It is a 3 over 2. So yeah, negative 1 over 2 minus 1, which is 2 over 2. So negative 3 over 2 like that. And now this 2 right here, this adds up. We can multiply this out with this 4, with this 2 over there. So that we'll get a positive. So we're going to get a positive 1 over 2. Actually, before, let's write this all in 1. So we're going to get a 1 times 3. And then here we're going to get a 2 times, well, 2 over 2 is going to be, 2 times 2 is 4. 2 times 4, so you can see the pattern rising that we were given. Now this is going to be, well, just k4 sine 4 of x, like that. And now the next one here, we have here 3 negatives, but then this is also a negative, and it's odd, so it's going to be negative. So that's even number negative, so you can see the pattern is going to be plus now. So all of them are going to be positive. And then this one's going to be 1/2, like this. And then this one right here, remember this is just 3 times 2. So then the 3 goes over here, is going to be 6, and then the 2 goes here, which is a 4. So this is going to be, you can see the pattern rising, 1 over 2. I'll put this full line. So 1 times 3 times it by 5, and at the bottom is going to be, well, a 2 times by 4 times by 6. So 3 times 2, 3 factorial is 3 times 2 times 1. So the 3 times it by 2 is 6, and then the 2 times it by here is 4, just like this one here. And then, yeah, you can see the pattern. Now this is going to be, yeah, so the negatives you already accounted for. Now it's going to be cubed, so 2 cubed is 6. So k6 sine 6x, and plus dot, box this out, and now that we have that. Now we just have to plug in our formula for sine. Alright, so now that we have this, now we could use our given formula for the integral of sine to the power of 2n of x, and evaluate the integral term by term from 0 to 1. So we can evaluate from 0 to 2 pi, not pi over 2. And actually, yeah, it is pi over 2. So we have to change all these from 2 pi to pi over 2. Scroll above here, this is pi over 2 over there. So they're all pi over 2s. So this is erase this is pi over 2. This is pi over 2, yes, my bad. Pi over 2. Pi over 2. And then this is going to be pi over 2. Yeah, so that's pi over 2. So we're going to evaluate term by term from 0 to pi over 2, and then we're given in the above formula. Yeah, so here's the above formula, yes, which is correct. 0, so integral from 0 to pi over 2 of sine squared, of sine to power of 2n of x dx equals to this here now. So it equals this pattern, 1, 3, 5, 2, 4, 6, where this is 2n is the max, and then 2n minus 1 is the max on top, and it's pi over 2. So we do that for every single term. And also notice that, yeah, so when you plug in, when you evaluate from the 0 is going to be always going to be just 0 in all these cases. The integral of 1 is x, and pi over 2 minus when you plug that in. When you evaluate it of x between pi over 2 and 0, you're going to have pi over 2 minus 0. And every single one will have it like that. Even the sine 1, sine of 0 is 0. So we can just replace it all with the pi over 2 version. So this is going to be t equals to, just do it all in one go, square root L over G, and now we're going to have, this is going to be bracket. So the integral of this one is going to be, integral of 1 is x, which is going to be pi over 2 when you evaluate it. The next one's going to be, well, these are just constants, so this is going to be plus 1/2 k squared. And now the sine squared, remember this becomes, so it's going to become 1, 3, 5, 2, 4, 6, but it goes to the 2n, and then there's a pi over 2, and this the top one is 2n minus 1. And where n is 2, yeah, so where n is 2, so that goes up to the maximum of 4. So it's going to be 2 times 4, and this one's going to be 2n minus 1, so 2 times, it's 1 times 3 over there, and then we get a pi over 2, like that. And evaluates from it. Yeah, from 0 to pi over 2, and that's already accounted for. Now the next one here is going to be plus a 1, plus a, and actually we made a mistake here. This goes to 2, yeah, it's 2n. So then if it's a 2, then n is 1. So yeah, that's a very important one. So if n is if you're going to be sine squared, that's going to go into, well, n is 1. So when n is 1, we get a 2 there. So yes, we start off at 1 over 2. Yeah, so this is just going to be 1 over 2. like that, and then yeah, so that's going to be our 2n. And then this is 2n minus 1, so 2 times 1 is 2, and 2 times 1 minus 1 is 1. This can be pi over 2 like that. And yeah, that's what we have for the this sine squared. Now the next one, and you can see here these are going to power up together. So this can be 1 squared, this is going to be 2 squared, as per expected. So now the next one's going to be over here, 1 times 3 over 2 times 4, and then k4. Now the next one, sine to the power 4, that's going to be 2n is going to be, well, n is 2. So that means we're going to have, yeah, it's going to go to the maximum here, which is our 2n. So that's going to be, this is going to be 4, 2, maybe 1, 3, and pi over 2 for our sine squared. And then the next one here is going to be plus, we have this part here. And you can see the pattern. 1 times 3 times 5 over 2 times 4 times 6. This is going to be kx. I mean k to the 6. Now this one here is going to be 3 times 2 is 6. So then n is 3. Let's try this one more time better. Alright, this is going to be now, it's going to go all the way to the 6 times 4 times 2. Then this one's 1 less than each one. 1 times 3 times 6 times 5. And these all line up with these ones over there. So that's what we get. We get plus dot dot dot. This is going to be, yeah, just like that. So we got rid of the whole integral to replace it with this. And now we can simplify this further by just writing this as equals to 4 square root L over G. And now we have plus pi over 2. Yeah, also we have this pi over 2 over here. Like that. And we're actually just going to, we could just actually factor out a pi over 2. So factor out a pi over 2. So take this out of there. So we're going to get a pi over 2 over here, so this becomes a 2. Yeah, 2 pi. Because, yeah, because we have this, this would cancel with this, becomes a 2, etc. On every single one of them. Yeah, so on every single one of them. So then we'll just have a 2 pi over there. And, yeah, so that's what we get. Let's put this a bit better. Equals to 2 pi when you factor out the pi over 2. And plus, now this one's going to add up. So we're going to get a 1 over, yeah, 1 squared over 2 squared. And then this is, yeah, just fix that up, and this is going to be k squared. Notice, yeah, these ones add up together, and all the pi over 2's are gone. And we're just left with, yeah, we factor it all out, it becomes 2 pi there. Now the next one's going to be, and then, yeah, all these ones are going to add up, or power up. 1 squared times 3 squared over 2 squared times 4 squared. And then this is going to be our k to the power 4. And lastly, here we get a 1 squared times 3 squared times 5 squared over 2 squared times 4 squared times 6 squared, like that. Yeah, that's what we have, and then we're just going to bracket this, and this will be our x, k to the power 6 plus dot dot dot. Yeah, just move it over here and box that in. Let's do a better box. Yeah, so that's that's pretty epic stuff we got here. And yeah, so this t equals to this, and we could see that this is actually what we were asked to solve, and I'll just double check that. So if we look at part A, so when we expand integrand as a binomial series, we can show that we will have 2 pi times it by square root L over G times 1 plus, and then you have this 1 squared, then a 2 squared, then 1, 3, 2, 4, all these squares, and there's the k squared, k4, k6, and there's the 1, 3, 5, 2, 4, 6. And then k power of 6. And you can see here as well. So you have 1 over 2, and those are both squared. And you have the 1, 3, 2, 4, all of them squared. Then 1, 3, 5, 2, 4, 6, all squared. And there's the k6. So this is exactly as we were asked. So let's put a check mark like that. Alright, so now let's look at part B. And part B states, notice that all the terms in the series after the first one have coefficients that are at most 1 over 1 over 4, and this is actually alluding to the statement as well. So if theta naught is not too large, the approximation right here, t is approximately equal to 2 pi times L over G square root, obtained by using only the first term in the series, yeah, is often used. So that's using this one right here, as I alluded to earlier. So that's just using that. And a better approximation is using 2 terms, which is using this over here. So the 2 squared is 4. And yeah, so that's using the 2 terms. There's a better approximation is obtained by using two terms, so we'll get this one here. And notice that all the terms in a series after the first one have coefficients that are at most 1 over 4. That is, notice here, so we have 1 squared divided by 2 squared, that's just 1 over 4. Now here, you're going to be multiplying by a fraction that's less than 1. Every single one of these, you're multiplying by less than 1. So these are getting smaller and smaller. So this is the biggest one, it's going to be just this 1 over 4. It's going to be our biggest value. Alright, so let's continue further. So now it says use this fact that this is at most 1 over 4 to compare the series with a geometric series and show that we'll have t is greater than or equal to 2 pi times L over G square root, and then 1 plus 1 over 4 k squared, which is this one right here. So that's this right here. And then show that it's going to be less than. So show that it's greater than this approximation, but less than 2 pi times, less than or equal to 2 pi times square root L over G, and then we'll have this 4 minus 3k squared divided by 4 minus 4k squared, which is a geometric series. So we can see that this part's true, but it's greater than this one because all these terms are positive. So all these ones are going to be positive. So that's going to be, yeah, so then that means if we're going to take only the first two terms, and then the actual Taylor, or the actual period is going to be bigger than these functions. I mean, bigger than this approximation because we have these extra positive terms. So let's just write that down. So the first of the two inequalities is true because all of the terms in the series are positive. Yeah, so we could just start off with this part right here, or just write it in our own way, right here. Just write it t equals 2, or is it approximately equals 2? Well, actually, it is equal to if we're using the estimation there, the exact one. So we're going to infinity. So this equals to, so t equals to 2 pi square root L over G, and then we have this 1 plus 1 over 2 squared, and this is going to be like that. And then this is k squared. I'm just going to add one more term, like this, 1 squared times 3 squared over 2 squared times 4 squared, k4. Here, just move it over and put a square bracket, and it's going to be plus dot dot dot, and like this. So now, well, this part right here is just going to be our 1 squared over 2 squared is just 1 over 4. 2 squared is 4, and 1 squared is 1. So that's our 1 over 4, and now this part right here is going to be, yeah, this is going to be this part right here. I'll just write it here, or just put it down, write it a bit better, like this. This is equal to, well, 1 over 4 times it by 3 over 4 squared, so it's a fraction. So in other words, this part right here is going to be less than 1 inside. So then this entire thing is going to be, well, 1 over 4 times it by a fraction less than 1, or a number less than 1. Is going to be, well, less than 1 over 4. So multiplying by. And they're all going to be like that for as you extend further. And now, the next thing is, well, from here and all the way past, these are all positive. These are all, well, the whole thing's positive. So then when you're adding more positive terms, then the actual value is going to be greater than when you only take the first two terms. So it's only going to be great. It's greater than when you take only these two terms like that. So I'll put thus, this is the first part of the inequality. Thus t is greater than or equal to 2 pi square root L over G, like that. And again, it depends on the value of k. If k is somehow 0, then these all vanish. So that's why we have the equal sign, just in case. So then this is going to be 1 plus 1 over 4, and this is our k squared over there, like that. Alright, so we got the first inequality now. So now the second inequality, for the second inequality, first recall the geometric series from our earlier video. And again, let's just go up to that question which one we were asked. So we're asked to go compare to the geometric series and to show that the period, the t is going to be less than or equal to this big giant function over there. But again, we're going to use this fact that the coefficients are at most 1 over 4. And once we recap on the geometric series, we can see that from an earlier video, the geometric series is summation from n equals 1 to infinity of ar power of n minus 1. And it just looks like this. So we have a plus a times r plus a times r squared, and it keeps going on. And this is convergent if the absolute value of r is less than 1, and its sum is, the summation is going to be a over 1 minus r. And again, for absolute value of r is less than 1. And if absolute value of r is greater than or equal to 1, the geometric series is divergent. So we can compare our Taylor series with the following geometric series. So let's just write this down. So our t equals 2, and then we're going to write this as 2 pi, just write our series for the period. So 1 plus 1 over 4. So this is, 1 over 4, k. Actually, let's just write it in the usual format for now. 1 over, 1 squared over 2 squared, k squared, plus 1 times 2 and 1 times 3 squared over 1 times, over 2 times, over 2 squared times 4 squared, k 4, and then plus 1 times 3 times 5, all squareds. Let's keep going. Squared over 2 squared times 4 squared times 6 squared. And then this is going to be k6 plus ... Put a close bracket. So now this one, we know that the terms are at most 1 over 4. So in other words, remember, these ones are all of these are going to be less than 1 over 4. So all of the terms for keep going on because you're multiplying 1 over 4 by fractions every single time. So this over here as well, you're going to be timesing by a number 1 over 4 times by a fraction less than 1 times by a fraction 5 over 6 squared less than 1. So that means if we just replace all of these with 1 over 4, this is going to be less than or equal to. It's going to be less than or equal to 2 pi square root L over G. Then put this bracket 1 plus 1 over 4 k squared plus 1 over 4 k 4 plus 1 over 4 k 6 and plus ... Yeah, now if you look at this part right here, so we have this 1 over 4 k squared, and then this is, it keeps going on. This is a geometric series right here, where the first term, we could just ignore this one, we could look at this first term. So if we have our a is just 1 over 4 k squared, and then this is going to be, our next term is going to be, multiplied by r, and r would be just k squared. So if you look at it like here, this part right here is a geometric series. It keeps going on. So this is a geometric series, and it has a is the starting one is equal to 1 over 4 k squared, because you're always going to have this 1 over 4 k squared in every single one. But now these powers just go up by k squareds. So the r is going to be increasing. R is going to be k squared and k4, etc. So, and then our r is equal to k squared. And also note that k, remember, because we have to make sure that r, absolute value of r, is less than 1 to make sure it's convergent. This is equal to number what we were given all the way up above in the earlier part. So we're given that where, let's scroll up here. So where k is equal to sine 1/2 theta. So let's keep going. So this equals to this equals to sine squared, because we were squaring it, 1/2 theta. 1/2 theta naught. Like that. And now this part here is convergent. Well, this part is going to be less than 1. So we get to assume that, we don't have angles of 90 degrees, and we will graph this out. So just recall, so this part right here is less than 1, so it's convergent for this period, or this domain. And again, recall that the sine function, you'll have sine like this, etc. Just going to call this theta, and this is going to be our our sine. This sine theta, and again, we're just going to be going like this. Remember, the value is going to be between 1 and -1. Yes, but move this down. So it's between 1 and -1. So the absolute value, and you're squaring it. So this absolute value is less than 1, and when you square, it's going to be positive always there. So basically, we're only going to be looking at it when it's not at this very top part, and with the pendulum, so when it's not 90 degrees, it's pi over 2, like that. And I'll just put a recall right here, just to note. So then we have this scenario right here. So we have our r is less than, less than 1. So absolute value of r is squared, so it's always positive over there, and yeah, that is what we have. Yeah, so thus what we get now is, well, now if we look at this part right here, and I'm just gonna box this out like that, and here I just moved it over here and just put another circle around it. So now what we get is, well, let's just bring this all the way down. So if this is a geometric series, we could sum it up by this. So that just equals to a divided by 1 minus r. So thus t is going to be less than or equal to 2 pi square root L over G times it by 1. So that's just 1 plus this whole thing is just going to be a over r. So plus a over 1 minus r. And that's the sum of the geometric series. Yeah, so that is what we have. So now let's start replacing it with our values. So this is going to be less than or equal to, alright, 2 pi square root L over G, and it's going to be times it by 1 plus a, which is our 1 over 4 k squared. So let's just write that above. Yeah, so we have, 1 over 4 k squared. I'll just write it as k squared over 4, and then divide this by 1 minus, and then r is just k squared. Like that. Yeah, so this is what we have, and now we just simplify it further to get it like the terms or the question wanted us. I'm going to do is I'm going to multiply this part right here by the denominator and the numerator like that. So then, yeah, I'll just multiply it by 1 over k squared times it by 1 over k squared, so that we get this going to equal to less than or equal to, just put this whole thing. Yeah, so what we're going to get is a 2 pi square root L over G, and then we're going to get a giant bracket. I'll just put this like that. 1 minus, so the same common denominator, 1 minus k squared plus k squared over 4. Divide this by 1 minus k squared, like that. And now we could add these to this k squared part, because this is just k squared by itself. That's equivalent of writing, well, 4 over 4. Yeah, 4 over 4 k squared, same thing, it's just going to be 1. So that we could add these up, so negative 4 plus 1 is going to be negative 3 over, yeah, then there's divided by 4. So this equals to, now this is going to equal to 2 pi square root L over G, and let's see what we can get now. This is going to be 1 minus 3 over 4, so when you subtract these or add these together, k squared over 1 minus k squared, like that. And now to get rid of this denominator of this 4 there, yes, just multiply top and bottom by 4. 4 over 4, so that this cancels out over there. So then what we're left with is, finally, we're left with is t is less than or equal to 2 pi square root L over G, and then we're going to have this 4 multiplied inside goes to 4 minus 3 k squared, divide this by, this 4 goes into here, 4 minus 4 k squared, which is exactly what we were asked to show. So this is less than it. Thus, sum it all up. Thus, t is going to be less than or equal to 2 pi square root L over G, and this is going to be our 4 minus 3k squared, 4 minus 4k squared, and then this is going to be greater than or equal to, just move it down here, it's going to be greater than or equal to our earlier approximation, which was just above here. So again, this is just using the two terms. It's going to be greater than 2 pi square root L over G, then this is 1 plus 1 over 4k squared. So that's the only difference. So we're going to get 2 pi. So t is greater than 2 pi square root L over G, and then we're going to have a 1 plus 1 over 4k squared, like that. And yeah, so this is our full inequality, and we can go and scroll up, and this is exactly what we're asked asked to solve. So the number is 2 pi times L square root L over G, and then the only difference between these two is these inside is going to be 1 plus 1 over 4k squared. And this one's got the 4 minus 3, and this one's 4 minus 4. and k squared on the top and bottom is to scroll up. And yeah, we're back to where we started. Yeah, so here's the question B. Yeah, so we have the 2 pi square root L over G, same sides, and then we have this 1 plus 1 over 4 k squared, and then this 4 minus 4, 4 minus 4, and then k squared on top and bottom. Yeah, now let's look at part C. So it states, use the inequalities in part B to estimate the period of a pendulum with L equals 1 meter and theta naught equals to 10 degrees. Then it says, how does it compare with estimate T is approximately equal to 2 pi times L over G square root? In other words, how does it compare with just using the first term to get, just to get this approximation, using just the first term, like that? And then also, then it says, what if theta naught is equal to 42, and then compare that. So let's just go here. This is going to be just a bunch of calculations, and I'll just do that all with OneNote. My OneNote calculator. So we substitute L equals 1 meter, and then then G is also going to be equal to 9.8 meters per second. So calculus book didn't bother with the units, but yeah. So anyway, so it's L equals 1, G equals 9.8, and K equals to sine theta over 2. So that's just what K is equal to, and in this case it equals to sine 10 over 2, because remember we're choosing theta not equals to 10 for this case. That's what we were given. And then this equals 2, and this is going to be, and my calculus book is in is in degrees. I mean, my OneNote calculator is in degrees, so just press space. We get this big giant number over there, 0.071555, but I'll just round it up all the way until, round up to the 6. That's rounded up over there. Yeah, because the solutions manual rounded up to the 1/6. And the inequality from part B becomes, so this whole thing becomes, and you can just write 2 pi times square root, L is 1, G is 9.8, and then times it by 1 plus 1 over 4 times k squared. So k is going to be this value here, 0.08716. And when you calculate this out, we get, let's see what this exactly gets. And yeah, we get this big giant number over there. And then, so we round it down, so just remove a bunch of zeros. And yes, we can round it down to that. And that is what we have. Yeah, so that's what my solutions manual does. So now we'll have the next one here. It's going to be 2 pi times square root, again, this whole thing, 1 over 9.8, which is L over G, times it by 4, and then we're going to have a bracket. Yeah, so we're going to have 2 brackets here. So 4 minus 3 times it by this k squared, so 0.08716 squared, and then the bottom is 4 minus 4 times k squared. And then this equals 2. Put it in this, and you see the calculator space equals to that. And it's rounded all the way down up to the 3 right here. So that's 5 decimal places. So now T is going to be between 2.01090 and then it's going to be greater than it and less than 2.01093. Yes, so T is approximately equal to, and take the average, or calculus book just takes average, or just removes this last decimal place and says 2.019. So T is approximately equal to that. And the estimate, now if you use the estimate with just the one term, which was, when you have just the one term, we just remove the entire, we remove that. So we just use this like that. That's going to be 2 pi times square root L over G. So the estimate, the estimate is approximately equal to, or the estimate period is approximately equal to 2 pi, 2 times pi, let's put this all in the calculator in one go, times square root L over G, which is 1 divided by 9.8. This equals to, 2.071. Let's put this space, 2.07, and then calculus book just rounds it up to the 1. Yeah, just rounds it up. And then there's 8 rounds up to the 1. Differs by, then you'll have, take the difference right here to 2.0109, which is just the, estimate from these two. Just the calculus book just takes it this. Yeah, they just they take an average and they round it down for some reason. But anyways, this is what it is. And then this differs by. So if you take the difference, so this is the difference between the approximation above, using both of the Taylor and the using both of the Taylor series and the geometric series. Yeah, the Taylor binomial series. We get 2.0109 minus 2.0071. And then divide this by 2.0071, which is, this is a smaller one, just to get the difference of it, then times by 100 to get the percent, you basically get the percent change. So the difference divided by this one here, and then times by 100 equals to 0.1893. like that. Yeah, so we get that, and then this is a percent because we have this times by 100. So this is approximately equal to 0.2%. So in other words, this is 0.2% difference from this one right here at theta is equal to 10 degrees. So at theta is equal to 10. Yeah, so that's what we have. So if theta naught is equal to 42 degrees, then k equals to, well, sine 42 divided by 2. Again, this is in degrees. And my calculus in degrees, so we just do that. And we get this value right here, and the calculus book just rounds it up all the way to the 6, 7 becomes 7. So rounds it up over there. And the inequality becomes, and just write this down again, so 2 pi square root L over G, which is 1 over 9.8, times by 1 plus 1 over 4, and this is the k squared. And this we get over here, 2.07153, space, yeah, and then 53 just rounds it all the way to the 5 decimal places. And then the next one is a geometric series. We have this the same 2 pi square root L over G. Then 4 minus 3 times k squared. And then divided by 4 minus 4 times k squared. And this equals to 2.018. 2.0813. And just rounds it up to 7, rounds it up to 3. Like that. And then put that in between. So then t is going to be greater than this, but less than this. So it's greater than or equal to this part here and less than this. And now if you take the average of these, so add these up together. So 2.07153 plus 2.08103 divided by 2, we get this, just take the average, 2.0763. And the one-term estimate is the same. Remember, this is the one-term estimate. Scroll up here, that's the one-term estimate. So we're going to compare it with that, and the discrepancy between the two estimate increases too. So now we take the difference of this one, the exact one. Yeah, this is the two-term approximation, and in between the geometric one. And then minus 2.071, which is the one term right here. Then divided by this one term. Then times by 100. See the difference between the one term and this one. We get 3.4478%. In other words, 3.4% difference when the angle is theta not is equal to 42 degrees. And but when angle is 10 degrees and the difference is only 0.2. So in other words, when it's small angles, we could just use the one term. So for small angles, we could just look at this only, and it's pretty decently accurate. And then as you get bigger angles, you're going to get off by several percent, 3.4%. But again, depending on the application, even this is probably good enough.